Okay, I think we're live now. Hi, everyone. Welcome again to today's Topos Colloquium. We are very pleased to have Jared Culbertson from the Air Force Research Laboratory. And today he's going to be talking about applying categorical thinking to practical domains. And we're very excited to hear about that. So please, Jared, whenever you're ready.
Thank you. I want to start out by thanking Xiaowei and David and the entire group at Topos for this opportunity to talk. I'm really excited to talk with this group today. This is sort of a strange talk for me. I spent some time thinking about what I would like to share with you that would be appropriate for this forum, and I ended up at sort of a weird mix of topics. And so hopefully it's not too disjointed, but hopefully it'll be both interesting and valuable for you. I do want to point out that a lot of this work, or really all of this work, is joint work with a variety of folks, and I'll try to point out on the individual topics of who was involved in the different collaborations. So the plan is sort of to highlight three main areas that I've thought about really over the last 10 to 13 years in working for the Air Force, and thinking about categorical probabilities, some data clustering, and then hopefully spend the bulk of the time on some of the robotics work that I've done in the past. So I wanted to start by, my formal training is in algebraic geometry and representation theory. So when I was in grad school, I was studying, reductive complex algebraic groups and their representations, and building on work by Delene and Bezrikov to think about things like coherent sheaves and Poisson structures and intersection cohomology, these sorts of things. But now I'm working, as Xiaowei mentioned, for the Air Force Research Laboratory and in an AI group called Act 3. And so we do a variety of things, starting from things that use deep reinforcement learning to fly real jet aircraft. So this is a picture of a modified F-16 that we had a group that had an AI agent that flew last December out at Edwards Air Force Base at the test pilot school. And did some formation flying and similar sorts of things out there. We're also training lots of agents to perform multi-agent spacecraft inspection problems. So if you think about having a satellite that might have taken some damage, and we want to be able to inspect that and see, what appropriate responses might be to that, we're trying to develop solutions there. Also, recently we've been getting into thinking about open-ended learning and how you could train populations of agents to learn novel behaviors and do this in new ways and do it more quickly. And then we also have a group that's focused on neurocognition. So understanding mechanisms of how the brain works, and also then how we can think about translating that into AI technologies and incorporating it into the other things that we're doing. And so when I started at AFRL, it became pretty clear that modeling uncertainties was very important and fundamental in almost everything that we did. And Kirk Sturtz, as a collaborator of mine, really taught me about this work of Lavier back in the 1960s, and then building on from there, he had a seminar with Huber, and Gary published some of this work in the 80s, I believe. And then there's been lots of follow-on work. The probability monad has been rediscovered many, many times under different names. But they're all essentially the same. And so the idea is that if you think about taking measurable spaces, and you're just going to map a measurable space to all the probability measures on that space, and then on the morphisms, it's pretty simple. You're just taking a probability measure to its push forward measure. And so this defines a monad. And if you look at the Kleistley category of that monad, this also has a very nice description. And so here, the objects are, again, measurable spaces, but the morphisms are sometimes called stochastic kernels, or regular conditional probabilities, or the ideas that you're taking a set in the sigma algebra on the codomain and pairing it with a point in the domain, and then getting a probability out of that. And so composition has been given by marginalizing over the intermediate space. And so this all works very nicely. It's very beautiful, and there are lots of variations, as I mentioned, where if what you care about is just Polish spaces or other, for example, for us, we wanted to restrict to certain finitely generated sigma algebras to make some of the computations more tractable, and so this all goes through in those different settings, and so what most of our work, the work that Kirk and I did here, was in trying to translate really known results into this sort of language. And so thinking about, well, what would conditional expectation mean in this sort of language, or what does a stochastic process look like? And the primary work that we did was in trying to understand and translate Bayesian, really Bayes' law and Bayesian reasoning into this language, thinking about what the existence of a particular, how the existence of a particular morphism could encode Bayesian inference. And so, we came up with diagrammatic expressions for parametric and non-parametric stochastic processing models for there, and also hidden Markov models. But I'll be really honest with you. This was extremely useful for me in trying to translate something that I didn't know at all, which was probabilities and measure theory and some of these things that I had not spent a lot of time studying up to that point, into a language that I could understand. So for that part, it was really good. We, in my mind, did not really accomplish the sort of goals that we set out to do. So we really wanted to find new algorithms. That was our goal when we started that work, was to say, well, if we could express these ideas in a more abstract language, that we would gain some insights into how we could incorporate other ideas and have some algorithm development there. That really didn't happen for us. And we also wanted to generalize beyond measurable spaces to think about, well, let's say you want to reason about uncertainty with mathematical objects that really, where yes, you can put them into a measurable setting, but maybe that's not a natural thing to do, and to be able to encode that in a more general way. And we had some sort of trivial examples of that, but nothing that was very impactful. And so I'll be honest, this was wholly like unsatisfying to me, the bulk of this work. And it was a lot of effort into trying to do this translation problem. But I will point out that I'm more optimistic now than I was if I'd given this talk 5 or 6 years ago, because recently there's been some very interesting work by different groups looking at say how you can apply these ideas, not just our work, but of course there were many people who are thinking about these sorts of things to things like quantum systems. And so there are folks working on like free energy principle and understanding what the asymptotic behavior of systems that follow the free energy principle and how they can be modeled using this sort of language, and also thinking about conditional distributions in quantum systems. And then Dan Scheibler has been doing some very interesting work in a variety of aspects of thinking about how to apply these sorts of things in different aspects of machine learning. And so I'm maybe, while not wholly satisfied, this is, as I said, this is I'm very optimistic about where this work is headed, and I think there's some exciting things going on there. So the second area that I wanted to overview was some work that we did in data clustering. And for those of you who aren't maybe familiar with this idea, the general idea is that you have some data, and here it's presented as say points on a plane, and it's generally very unstructured data, and you want to think about how you could add structure to that data by thinking about grouping it in different ways. And traditionally, primarily in partitions. So you want to take your data, and in this case, so thankfully is easy, and think about how that could be grouped into these disjoint partitions, disjoint sets, and make up partition. And there was not very much axiomatic work that has been done in this area. One exception is the work of Feinberg in the early 2000s. And Feinberg showed us that there's no consistent method of clustering if you're using partitions. And by consistent, he had these 3 axioms that he wanted methods to be able to satisfy. The first was a richness condition. And so this is important because if you don't have some sort of richness condition where so for him, it was that all partitions of a given set are realizable by that clustering method. But if you don't have any condition of richness, you can just cluster everything to a single, one big cluster, or you could have all of your data points always be clustered into individual clusters, and then it doesn't matter whatever else you want to do works because you're sort of too constrained. And of course there are relaxations of that, but if you take that all the way to the extreme, the richness that he was considering was that you can get any partition of that set. And then also that it's scale invariant. So if you zoom in and out of your data, that it shouldn't change the way that you're clustering that data. And then there was a transformation constraint where if you think about a given clustering of the data, and if you reduce the distances within the clusters, and you're allowed to extend the distances between clusters, between points in different clusters, then the idea is that you shouldn't change the clustering. And it's not too hard to see that these aren't consistent with each other, that there's some issue here, and that's the reason you get the impossibility result here. For example, if you're able to, in the shrinking of the things within a cluster, the data points within a cluster, if you're allowed to reconfigure them in whatever way you want, which is fine by this rule, then that doesn't really work very well with scale invariance. And so that's pretty clear. But it was still an important observation nonetheless. And not long after that, a few years after that, Carlson and Momoli had this very nice work on thinking about categorical approach to clustering. And so they wanted to express these sorts of consistency conditions, but rather than in the sense that Feinberg used to express it as a functional reality. And so the category of metric spaces with non-expansive maps goes back at least to Isbell in the 60s. And the philosophy here is that if you're wanting to do clustering and you have some data and you are allowed to decrease the distances through some processing. So if your function f here is some processing of that data, then you can decrease the distances, but you can't increase them because you shouldn't be able to increase your ability to discriminate between data points through processing the data. And so this sort of philosophy of using functional reality of these methods to encode consistency with respect to these sorts of maps, we thought was a pretty interesting one, and I think was very insightful by them. I think the other thing that was really important about this work was that they took this well-known correspondence between dendrograms, which you see an example of a dendrogram in the lower left here of a hierarchy of partitions. So they said, well, what if instead of looking at single partitions of the data, we looked at hierarchies of partitions, and then can we get away from this this impossibility result? And there's an equivalence of categories between the category of ultrametric spaces, which satisfy a strong triangle inequality, where it's really a max condition, and dendrograms. And so then you can realize single linkage clustering as the unique functorial method of projecting from arbitrary metric spaces down to this category of ultrametric spaces, which are equivalent to dendrograms. And so there's a nice connection here with minimum spanning trees as well, which gives you an efficient algorithm for both computing the dendrogram and the associated ultrametric. And so this is very nice work. And so what we wanted to ask was, well, is there are there other useful categories where if you relax some of the conditions that Carlson Momoli were using, that you could find other interesting methods of clustering beyond single linkage? Because single linkage has both some negative chaining effects that can happen with it, and also there's quite a bit of information loss, which in a information theoretic sense that could be made precise, going from an arbitrary metric space down to an ultrametric. And so we wanted to know, are there sort of intermediate things that you could do in between those? And what we found was that if you expanded the idea of dendrogram, and instead of thinking about just hierarchies of partitions, you allowed yourself to think about hierarchies of covers. And so you have overlapping clusters now. And so we call these hierarchies of overlapping covers sieves. That there's an equivalence that generalizes the dendrogram to ultrametric equivalence between the category of sieves and the category of weights, where you drop the triangle inequality requirement for metrics. And and moreover, not only is there equivalence between those categories, but you can characterize what constitute nice subcategories of the weight spaces, and there's a direct correspondence to unique clustering maps on the sieve side. And so what this really comes down to is the fact that the category of weight spaces is fibered over set. And if you think about what would make subcategory nice, it's going to be the subcategories where the fibers are directed complete posets. And so that means that if you take any given weight and look at all of the weights that it dominates, that set is closed under Suprema, undertaking Suprema. And so, and that's exactly the algorithm of how you define the projection from the weight spaces to some subcategory, is you find the largest one that's in that subcategory that is dominated by the original one. And so this was very nice. We really liked the picture that you get here, and it sort of things work out nicely, including this idea of stationarity of functoring with the sieve, so that if you want to, if you cluster something more than once, so you can cluster and then you can go back to weight and then cluster again, then you should get the same thing. And so this all works out nicely. And there's a nice corollary that says that there cannot be a clustering projection to cut metrics, which is a particular class of metrics that are very simple to describe. But and for which people were looking for some projections here, and so that was a nice result. But reality is that no one uses this theory, and there are a host of reasons for that. I'll highlight just a couple of them. One is really algorithm efficiency and software implementations, which was not something that we focused on at all. So we were almost entirely focused on the theoretical aspects of this work, and so I spent way too much time trying to convince people that they should care about these things. And but I think there was a more philosophical problem here, and that is that consistency in the way that we were expressing it was not something that practitioners who use clustering algorithms actually cared about. And so there was sort of this mismatch between what practitioners really needed to be able to do exploratory data analysis and the sort of unsupervised clustering that they would like to do, and the tools they already have, and what this brought. And this the bottom line was really that we came up with some nice theory that there are connections to very interesting things here, cubical complexes, injective envelopes of metric spaces. So it's some really nice, interesting mathematics. But when you try to develop the theory first and then go and look for applications, I think that this really rarely brings very much near-term value. And so this was a lesson that I think we had to learn very acutely in this work, and I think is an important one. So where I'd like to spend most of my time today is in talking with you about some of the work that we did with Dan Kodacek at Penn. I believe Dan gave a talk at this colloquium last year, and so I'm not going to go into a lot of details about the robotics side of the collaboration, but rather focus more on the mathematical side. But Dan and his group have been able to do some really amazing things with the robots that they have developed there. So they mostly work with these quadruped robots, and they've been able to get them to do all sorts of things, from climbing across these metal ladders that, like in the top, or manipulating objects, opening doors, climbing chain link fences, and they've really been able to do this not just in ad hoc ways, but in robust, repeatable ways that are very very good. And so this really comes from, and it's really due to this emerging calculus of behaviors that Dan and his group have been working on, that comes from a very deep understanding of the dynamics of these systems, and carefully controlling the coupling of those systems and the way that these systems interact and can be sequenced. And so they spend a lot of time thinking about how to model the systems at different levels of abstraction, and how those can be tied together and connected in a variety of ways to do some really incredible things. And so our task was to think about how we could formalize these sorts of constructions that Dan and his group were doing with robotics into a formal mathematical language. And so that came down primarily these three ideas. And so the first one was thinking about transformations. And so when Dan and his group want to think about a physical layer, and I'm sorry, it looks like the graphic didn't quite come up here. The last two here look the same with the map layer and the model layer. You should imagine some slightly abstracted thing in the map layer, and then the model layer is really a point sort of navigation problem here, so that you can go from a more and more complex scenes to more and more abstract simplified scenes, but do so in a consistent way that respects the dynamics at every level. And the next piece is sequential composition. So the way Dan and his group think about this is in terms of these sorts of funnels of dynamics. So you want to think about, well, what would it mean to apply different behaviors in sequence? And so if a behavior is modeled as some sort of dynamical system that you can think about as some large funnel, so no matter where you are in this large state space, it will funnel you down to some desired state and dynamics, which then you can switch to another funnel that will then take you from that one to some other place, and then you can think about sequencing these. And so the question was, well, how could we formalize those notions? And so I'll tell you about the work that we did there. And then finally, is this idea of templates and anchors. So this is goes back quite a ways to some biologically inspired work of thinking about how animals are able to do things like control the very high degrees of freedom that we have in the sorts of systems that we exist in, and be able to have very low dimensional templates that are then embedded in an attracting way in a high degree of freedom systems, and so what that would look like as well. And by the way, I don't think I mentioned this at the beginning. I'm very happy for anyone to interrupt me at any time with questions, or if you want to put things in the chat, feel free to do that. And Shelley tells me he'll let me know. So let's get more concrete about this. So what is a hybrid system for us? So a hybrid system is really it has an underlying directed graph, and for us we're working in the category of at least one equivalent to the category of directed reflexive graphs. And so you can either think about that as there being a distinguished edge at every vertex of the graph, or you could think about it as you being okay to in the morphisms to map edges to nodes as well. So either one of those are equivalent ways of thinking about that. And so you have this underlying directed graph, and then at each node of the graph, you're going to basically have a continuous flow. And so if you think about a hybrid system is really one in where you're mixing both the continuous flows and the discrete flows. And so you're going to say, go to a node, flow for a bit, and then hit a guard set, and then jump to another node, flow for a bit, hit a guard set, jump back to another node. And so the way to encode this in this sense is having this graph, which is where the nodes index the continuous modes and the edges index the reset maps and the guards that describes the discrete dynamics. And so a simple example is the one of a rocking block here. So if you think about just a rectangular block here that's sitting on a plane and is tipped up on an edge, and it's going to rock back and forth and hit the ground on one side and then go back to the other side. And so there's some angular velocity here, and that angular velocity is being damped when it hits the ground, and it's going to bounce back with a little bit smaller angular velocity. But as it hits the bottom, it's going to have this instantaneous change from, say, going to the right to now it's going to be swapping and going to the left. And so you really have this two-node system where it's just going back and forth from going from the left to the right to the right to the left, and you can track the dynamics in this way. So these sorts of systems are extremely expressive in the terms of what types of physical systems that they can represent, and have become very important in not just robotics, but in many different sorts of applications. And so these are the objects of our category that we're going to be looking at. The morphisms are not surprising. So I think if any of you sat down and decided to follow your nose and write down what the morphisms would be here, you'd come to the same conclusion here. So and this generalizes the idea of a classical semiconjugacy. So if you have classical dynamical systems, you want to think about a semiconjugacy as a map between those systems that really maps the flow lines of one onto the flow lines of the other. So this is, in some sense, when semiconjugacies exist between systems, it's saying that there's a consistency between the dynamics of those systems, and that they can be sort of consistently mapped to one another. And so here you get an underlying graph morphism on the underlying graphs, and then at each node you also will get smooth maps between the continuous sets, and they satisfy the obvious sort of compatibility conditions here, both in the continuous flow compatibility and for the reset maps that these diagrams can use. Things like conjugacy, submersions, embeddings are all very straightforward here once you have these basic definitions. One thing that I will point out is that there's some technical tools that are needed to deal with what the sorts of practically relevant subsets of manifolds that come up in the kinds of constructions that we want to do. So for example, we're going to want to work with fiber products of manifolds. And if you've studied this sort of thing before, the manifolds are not very well behaved with respect to fiber products in general. So of course you can take fiber products along smooth submersions, but you have to be careful in some cases, because it's easy to get into situations where you no longer have smoothness conditions everywhere. So there are a variety of different ways of dealing with this. And so I'll comment a bit later on why we chose to develop our own approach here rather than work directly with something like manifolds with corners. But this development that we worked on here allowed us to really think about flows on arbitrary subsets of a manifold rather than needing a flow to be defined over a whole smooth manifold. And it comes down to this idea of a filtered co-limit over the smooth manifolds containing a particular set. And so this was important for us. So these are the morphisms in this category. And so this does indeed make a category. You can compose these squares that I have here vertically, so everything works out nicely there, and it's nicely associative. And what this allows us to do is to encode properties and aspects of these systems as semiconjugacies. And so, for example, we can think about what an execution of a hybrid system would be like. And so if you're familiar with classical dynamical systems, where you have the integral curves that define the trajectories of the given an initial point where that point will flow to in that system. So in a hybrid system, you have the same sort of thing, but instead of just flowing, now you're going to flow and jump and flow and jump and jump in. And we do require that we don't have any Zeno behavior here, which would be if you had infinitely many jumps in finite time. And so we make that simplification. But you can express a hybrid time trajectory as a hybrid system itself in the way that I've shown here, where if you think about this hybrid time trajectory where you're going to flow up till time tau 1 and then jump instantaneously at tau 1 and then flow until tau 2 and then jump there and then jump again and then flow again. So this is a 5-node graph with just the single edges between each of the nodes, which then encodes that trajectory as a hybrid system. And then looking at a semiconjugacy of that hybrid system into a given hybrid system that's compatible with it, it enables us to encode all of the semiconjugacy, all of the executions of the codomain system. And so this is a way of thinking about executions of any hybrid system just as Hom sets in this category. So once we have this idea of hybrid executions described in this way, we can think about what it might mean to subdivide a hybrid system. And in this case, this is important for us when I'll show on the next slide in defining this template and anchor construction. But the idea is that if you take any hybrid submersion here, and this is just an analog of the classical subversion. So P here is a hybrid submersion from S to H. And if pi is any execution of that hybrid system, so any hybrid trajectory in that system, then there should be a lifting property through this fiber product construction that allows you to have a refinement of that hybrid time trajectory. So sigma refines tau, and there exists some sort of execution from sigma then into the subdivided system. And so the first example of this are hybrid time trajectories themselves. So if you think about classical time just as the non-negative real line with a constant flow on it, then you have a hybrid subdivision from any hybrid time trajectory where you're sort of thinking about adding in these jump times down to the classical setting. And so this allows us to do things like in the second example here of, say, slicing a continuous system. So if you take some classical dynamical system and you take some codimension 1 submanifold that is transverse to the flow everywhere, then you can slice the system and just at the boundary points add in reset maps that map you back and forth. And so it's really the same dynamics. And that's really the key, is that it's a way of expressing the same dynamics, but now I've added in these almost trivial reset maps that allow me to do this in a different way. And so, okay, so why would you want to do this?
Sorry to interrupt. We have a question from Kevin. The question is that is the active set likely to be just the union of the guard sets for all the edges out of a given node, or does it have some independent meaning of its own?
Yeah, that's a great question. Yes, usually the active set is the union of both the flow set and the guard sets. We didn't make it a requirement that is the case because there are some technicalities where sometimes you might end up with a larger active set than through some construction than the union of the guard sets and flow sets. But that's certainly the idea there, is that the active set is just a way of keeping track of where interesting things are happening in this larger ambient manifold. Yeah,
thank you, Jared.
Cool, thanks.
So now we can define this idea of a template anchor pair just as a span where so if you remember the idea is that this low dimensional template should be something very simple, some sort of very simple sort of dynamical system. And then we want to be able to subdivide that low dimensional thing into something that is sort of the same dimension, but maybe split into multiple components that can then be embedded into a larger ambient system in an attracting way. And so if you think about this sort of construction, well, for one thing, you can do the usual sorts of things that you do with spans and get, you can weakly associatively compose these things so that, if you've got multiple templates that you want to stack hierarchically, you can do that in an okay way. And it allows you to do things like, here's an example of just a vertical hopper robot. So you have this robot that's just jumping up and down on the ground, and it sort of has these two modes to it. One is a stance mode, so that's where it's actually in contact with the ground, and so it's undergoing some dynamics there that have to do with the springiness of the robot and how much momentum it has and all these sorts of things. And then it has a flight mode to it, where the only thing acting on it in the flight mode is gravity. And so you can model that just as a reset map, because once it's in the air with whatever state and dynamics that it has, it's going to be deterministic of where it's going to land, or what state it's going to land in. And so you can model that in that way. And so we're able to think about the low-level system as just this periodic orbit that you're just continuously traversing. And then you can subdivide that orbit now into an interval together with a reset map, and then embed that into these two pieces of the full dimensional hybrid system. And so this is sort of a general idea for how this template and anchoring would work is that you can break up, you can take very simple sorts of dynamical systems, break them up into the pieces as needed to embed into the more complex hybrid dynamical system, but still retain this idea of what a really a hybrid limit cycle should mean in that larger system. So next I'd like to work toward thinking about sequential composition, but before we get there, we'll have to revisit some tools from classical dynamical systems. And Xiaowei and I were talking about before we started here that the Conley's fundamental theorem. This is a really nice theorem. Here is a statement from Norton that every flow in a compact metric space decomposes into a chain recurrent part and a gradient-like part. So this is equivalent to the existence of a strict Lyapunov function for any system modulo the thinking about attractors and repellers in the system. And so the really amazing thing about this theorem is that it doesn't matter how complex the dynamics are. So you could take whatever sort of chaotic attractors you have, whatever sort of strange things you have going on, as long as you're on, this has been extended past just compact spaces now, but the easiest case is to stay those on a compact space, that you can, whatever the dynamics are, you can sort of put boxes around the complexities, and then in between those things, it's basically just the gradient of some potential function. And so this is very nice because it allows you to analyze and understand very complex dynamical systems and think about abstractions of those things. And for us, one of the important things was Conley's understanding of chain recurrence, his development of chain recurrence, and particularly the epsilon T chains that he used. And so the idea here, this picture is a little fuzzy, but hopefully it's still intelligible. So if you think about, as opposed to a usual trajectory where you just flow along some integral curve, here you flow for some time, time t, and then you're allowed to jump by some epsilon over to some other trajectory, and then flow for at least t, and then jump, and you look at the limits as epsilon goes to 0 and t goes to infinity, so that you're squeezing down the neighborhood of how far you're able to jump, and you're having to flow for longer. And if you can still get from a point x to a point y through these epsilon T chains, even through that limit, then there's an equivalence relation between those points in terms of their chain recurrence, or their chain equivalence. And then so you can define the notion of recurrence based on that idea. And so just as Conley found it useful to generalize the idea of classical trajectories for his fundamental theorem, we found it really important to generalize the notion of hybrid execution, not so that it is not strictly based on flowing and then jumping in this precise way, but now you're allowed to flow, and you can jump either after you've flowed for time t, or after each reset. And so there's it's sort of a direct analog of the classical epsilon T chains that is better behaved in a way that I'll describe in a minute. But I did want to point out that one nice theorem that Paul Gustafson, and Dan Kotek, who were collaborators on this with me, and then Matt Kavalheim developed, was a way of, was an analog of Conley's fundamental theorem, but for hybrid systems. And so this is very nice. They did it by looking topologically at a system and taking suspensions and adding in tubular regions around reset maps, and then applying classical constructions there. So it's a very nice way of thinking about a hybrid version of Conley's theory. So with that in hand, we're able to define these directed systems. And so these are our cospans, where we think about, in this funnel sense that I was describing earlier, we think about there's some initial subsystem that you have, some initial starting location, and you have some final subsystem. And these could be, the initial subsystem could be very large, and the final system is often much smaller. And you want to think about the final system being an epsilon t sink in the larger ambient system H. And so you have these, the idea is that, wherever you start in H sub I, that you're able to ensure that, at least in an epsilon t sense, that you'll be able to flow into the final system in H sub F. And so this very explicit sort of depiction of the interfaces of these systems is important, because it allows you to do sequential composition of these systems in a way that is agnostic to the underlying system. And so the reason that the epsilon t chains are important is because standard hybrid executions don't compose well. So you can get in a position where, if you have all of your executions that go to, say, a single point, and that point happens to be a stationary point in the system you're composing with, and then you're just stuck because you can't get away from that stationary point. And so the ability to jump allows you to compose these things in a useful way. And I'll also point out that it is really important that these initial and final systems actually have dynamics themselves, that these are not just state spaces. So it's not just that you're describing an initial subset of states or a final subset of states that are appropriate for initialization and finalization, but rather that these are actually hybrid systems themselves, because it's often the case in real settings where it's not enough to say that you're in this state. You need to know what your current dynamics are in that state, in particular if you don't want to have to worry about timing conditions of how long you need to stay there and that sort of thing. So if you can just encode it all in the dynamics, then it's much cleaner. So you can put all of these things together then, and you get a nice double category of hybrid systems where the horizontal direction encodes sequential composition, and the vertical direction encodes semiconjugacy or transformations. And so there's some nice structural results here. These are Cartesian and co-Cartesian. If you allow, instead of, so here I worked with reset maps. If you allow reset relations, then you can get a framed by category. That wasn't critical for us, and so we didn't go down that road, but it was certainly possible. And this is really a lot of Paul Gustafson's work since then. So after Paul left working as a postdoc for me, he went to work as a postdoc for Dan Kodacek at Penn, and kept working on some of the how we could translate this work into a type theory. And so here's a very simple type theory for mobile manipulation that has operational semantics in this hybrid systems category. And so Paul, together with some of the postdocs and graduate students at Penn, were able to implement this. And there's a link to Paul's GitHub here that has a basic implementation of this. And they were using this to do some of the robotic simulations in Gazebo and other things there. And so I was really happy to see it. And Paul, I think, has gone on to do some even more interesting things with linear logics and connections with more complex type theories based on the same underlying hybrid systems theory. Okay, so what was really important for us, I think, in all of this work with Dan and thinking about these robotic problems, were thinking about abstractions and simplifications and being able to have Dan around to kick me in the shins whenever I wanted to do something that was not appropriate for his application. And so there were lots of points along this work where we had choices of either going for more elegant or abstract formulations, but instead opted for more grounded approaches. So for example, when I first started this, I really wanted there to be exponential objects in this category of hybrid systems. And so I started looking around at things like diffeological spaces or Frolicker spaces, which sort of solve that problem directly of how you can get exponential objects. But what was absolutely true was that there was no way that Dan was going to work with diffeological spaces when he's building his robots. And so it really didn't match the application. And so the same sort of thing with manifolds with corners, even the manifolds with generalized corners. There's a very nice mathematical theory built up around these. But for the particular applications, and I'll say particularly because of the notions of equivalences, because what becomes very difficult there is what the tangent spaces look like at those corners. And the decision that you make and how you define the manifolds with corners will determine what the dynamics what dynamics are available to you at those points. And so they didn't quite match up. And so it was one of those cases where we could have said, well, let's just make this simplifying assumption, and we're only going to work with hybrid systems that satisfy these things or have these nice corners or have these nice dynamics at those corners. But the reality was that that didn't match the way that Dan wanted to work with his legged robots that had physical contacts with the ground that were making and breaking all the time and were running upstairs and climbing chain link fences. And so it took some more time to develop this idea of smooth sets, but it ended up being appropriate for us. So a couple of other simplifications and things that were useful for us and not useful for us. So we tried to simplify things by let's make this problem really easy and just look at gradient systems on surfaces. And that led us to thinking about cobordisms and there was some very interesting mathematics there. And I still think that, for example, directed systems, for those of you who are familiar with those, I think that there are some nice connections with this work that could be extended in that direction. But it again, wasn't sort of the right abstraction for this because it took us in a direction that didn't bring value for the implementations that Dan was looking to do in his group. What we did find useful was that, for example, only looking at trivially coupled systems. So I talked to you about sequential composition. We did have some amount of so-called parallel composition, but only in an uncoupled product sense. And this was the case where, because Dan's group was very good at developing mechanisms for reducing crosstalk and basically decoupling systems on their end, it allowed us to make that simplification on our end, on the mathematical modeling side, so that there was still good alignment and still applied to the sorts of systems that he wanted to be able to model, even though we realized that it's not fully descriptive of the complexities that you could get into if you have fully non-trivially coupled systems. Again, I'll say that we did not allow any Zeno behavior. My favorite example here is Dan Guralnik came up with this diabolical example of Zeno behavior where basically you switch systems on a Cantor set or based on a Cantor set. So this is like the worst possible type of Zeno behavior you could have, because it's not like you have a one point where you could continue from that point. It's really horrible. So we just threw out those sorts of things, and that was okay because there are lots of interesting systems that don't exhibit Zeno behavior, and so that was not a problem. We restricted to non-blocking deterministic systems, which basically amounts to the analog of existence and uniqueness of integral curves in the classical setting. And so there are certainly hybrid systems which exhibit both non-determinism and blocking states, which are interesting, but there are again many that are not. So what we found was that this having someone to tell us which of these simplifications and abstractions were useful and which were not was absolutely critical to what we were doing here. And so I'd like to really leave you with just a few concluding thoughts here. And maybe I'll start with the last one since I was just there. That working with practitioners continually, to me, is absolutely essential to making these sorts of useful abstractions and interfaces. One of the things that we tried very hard to do in the robotics work is to not make the roboticists come to us, but to work with the mathematical objects that the roboticists were already working with, so that they would be more readily able to adapt those, even if there was a bit of friction there at times. I think requiring practitioners to fully understand very abstract mathematical objects is much harder than bringing the abstract mathematics to the sorts of objects that they're already working with. The second one, and I'll just go in reverse order here, is, when we were doing the clustering work, I was convinced that well, this is a problem that has to be solved, that we must bring formalization to every domain. And I think I'm much less convinced of that now, especially in domains where you're trying to find near-term value. That is often the case that in some cases there are existing tools that work well, and that the major roadblocks are not formalization roadblocks. They might be efficiency or other sorts of roadblocks there. And then finally, I'll say that we've throughout all of this work proved a lot of theorems that are of this form. Something can be expressed as whatever mathematical language that we're working with. And the reality is that many of the mathematical languages that we work in are highly expressive, and I'm much less enamored with these sorts of theorems of expressiveness now, unless they're accompanied by this meaningful machinery. So what is it that we can bring to bear from that field that we're using to express these things into, that can bring new insights, new approaches, new ideas? And I think that's really where, as a field, if we think about applying categorical ideas to different topics, that's really where we'll be well served to focus. So I think I'll stop there. Thank you.
Thank you so much, Jared. That was a really, really amazing sharing of your experiences. Thank you so much. So now we have some time for questions. If you have a question for Jared, please you can raise your hand, and then I will call you, and you can unmute yourself, or you can ask them in the Zoom chat, and I will ask them on your behalf. So let me see. We have I'm sorry about this. Let me just pull this down. We have a question from David. Is that right, David? You can unmute yourself. Sorry. Did I get it right? David, do you have your... No, sorry, James. James, you have a question. I'm sorry.
Yeah.
Okay.
Hi, Jared. Thanks for the great talk. I'm interested in, so you said, go to the application people, don't make the application people come to us. And then, so what are the things that we're computing about HDSs that you think are important to compute? And then what kind of algorithmic techniques are available?
Yeah, so to me, the reason that application in particular was sort of ripe for this type of formalization was due to this fact that they were sort of doing it already. If I go back to here, there was sort of already a calculus that was going on here that sort of was begging for a formalization, and this was being asked for by the roboticists who were saying, we're doing this, it works, but if we could formalize it in a better way or a more expressive way, then we would be able to know what the extents are of where it will work and where it will fail. And so to me, that's really where where we were able to bring some of these tools from like Conley theory in and apply them here to say, this idea of hybrid epsilon T chains as generalized executions was not something that the hybrid dynamical systems community was thinking about. But in going through the formalization process and thinking about what sequential composition should look like there, it sort of became clear that you couldn't do the type of either measure theoretic or probabilistic type of assumptions that were being used prior to that, and in this type of application of when you can compose things and what those sort of conditions can look like. And so I think that I don't know that I have a general statement that I could make about applications in general, but at least in this one, to me, it was the fact that there was sort of an emerging formalization already that needed to be codified.
Great, thanks.
Okay. I have quite a few questions of my own, but maybe I'll ask Yeah. So I really like what you said about the epsilon T chains, hybrid T chains. Yeah, really amazing way of thinking about dynamical systems. And it really, I do some work with spiking neural networks, and it really kind of gels with me because that's kind of how our brains are computing things. We have these events where we have spikes, and in between we have the activations where the potential is kind of going up in the cell and things like that. So it seems like these chains are also good for kind of like modeling things which are neural systems and maybe even in AI. So I'm just wondering like um so I mean there are many possible questions here, but maybe one of the questions is that this decomposition here, is there a way to learn those decompositions given maybe a system? Maybe you could have a learning system that could have certain kinds of states, certain kinds of states which are arising through learning. Is there a way that we can kind of decompose them into some kind of a chain like this so that we could actually use that for maybe reinforcement learning or other kinds of learning? What are your thoughts about that, Jared?
Yeah, I think that's a really interesting idea. Of course, there have been many works encoding classical dynamics in, say, neural network approximators. And so I think your idea of I have not seen this much in the hybrid setting. And so I think that that's very interesting. And I haven't thought very deeply about that, but I do agree that especially in things like brain dynamics, where phase synchrony and other types of aspects of the coupling of those different systems seem to encode lots of useful information and reflect the communications capability of the network. It does. I agree with you. It seems very interesting. I don't think I have any insights there at the moment though, but I agree. It's a very interesting direction.
Thank you, Jared. Are there other questions for Jared? Feel free to unmute yourself or raise your hand. So
we have one here, shall we?
Okay, yes.
Yeah, so while you have the slide up, Jared, so I missed a bit as you were going, but it seems like you're saying that basically your double category is motivated by formalizing these kind of informal equations. So I guess the systems you're drawing are systems and plus is your sequential composition. Is this times operation something that's kind of being formalized in your double category as well? I can't really see the.
Yeah, so that's a great question, and the times operation here is roughly a parallel composition, a coupled systems, and so this is the case where there are places where the roboticists are ahead of where we were with the formalization capability of being able to model some of those. In cases like these, where they were able to restrict the coupling to make it manageable, they can sort of do both of these behaviors at the same time in a coupled sense, but that it acts almost like an uncoupled system. And so those were the cases that we were able to model directly through the just the product structure in the category.
Okay, got it. So you've got a Cartesian double category or something like that? Or
You have a monoidal double category?
Yes.
Or,
yes. Yes, it's Cartesian.
Cartesian. Okay. Cool. Thanks.
Okay. Yeah.
Could you talk a little bit about future plans?
Oh, sure. So so my future plans, this is sort of a little bit why this is a strange talk for me. You could see most of this work was done several years ago. I've really, since doing some of this work, have tried to dive deeply into a lot of the reinforcement learning work and have not been further developing much of this. And so I've been trying to put on my practitioner hat and try to learn very closely what people who are deep into reinforcement learning and open-ended learning, how they think about these problems. And so we've been developing some some algorithms to incorporate things like intrinsic curiosity into reinforcement learning populations of agents. And so we have a paper that we're working on getting out with that. And also talking to a variety of people about what compositionality might look like in reinforcement learning. There's some very good work going on down at University of Texas and other places thinking about these things. And so I'm very excited about where that's going. That's probably where I'm spending most of my time these days thinking is about in those learning areas, how to bring in the sort of compositional thinking.
That's very, very exciting. Thank you, Jared. Maybe we should talk more. We have quite a few activities at Topos as well.
Great.
These things. So I think what I'm going to do now is I'm going to end the live streaming on YouTube, and Jared has told me that he has a bit of time to stay on in the Zoom chat for more questions or discussions. So let us thank Jared again for this really good talk, amazing talk.
Thank you very much. Happy to be here.
Thank you for your time, Jared. Okay, I'm going to end the live stream now. Okay, live streaming has ended.